Great. And so this last talk is, I think, delivered by Nicolas Chappe, monadic interpreters for concurrent memory models.
Can I start?
Yes.
Okay, thanks. So, one of the goals of this work is to define executable semantics of for a concurrent subset of LLVM IR. Okay, so LLVM IR is a compiler intermediate representation that is widely used. There are many programming languages that compile down to LLVM IR, and in turn, it compiles LLVM IR compiles down to many different architectures. Finally, there are many program transformations and optimizations that are defined on LLVM IR. This gives it a very central role in many compilation infrastructures, which makes it a very interesting starting point for a verified compilation infrastructure and to formalize its semantics. This is the whole point of the existing Vellum project. Vellum's goal is to efficiently model the semantics of LLVM IR in work, formerly COC. How it does it is by using a fitting library to represent programs in work, which is the interaction trees or iTrees library. The iTree library is designed specifically with large-scale programming language semantics, such as LLVM IR in mind. Vellum is based on it, but in its current state, there is no support for concurrency in Vellum. It's limited to sequential LLVM IR programs. And adding support for concurrency is no easy task. There is a lot of added complexity with concurrent memory accesses that can give rise to data races, for instance. And there is, in fact, a whole field of research dedicated to such concurrent memory accesses, which is called weak memory models. This is no easy task, but this is our long-term goal with this paper, which is to model the semantics of concurrent LLVM IR in work. For that purpose, we follow the Vellum method, which is to first create a fitting data structure for representing concurrent programs, which we called choice trees or CTree for short, and we presented it at Popol 2 years ago. And then we get to the present paper, which is to use this new data structure to model a concurrent subset of the semantics of LLVM IR based on CTrees. Okay, so I first need to detail the basics about choice trees. So this is an infinite, or more precisely, co-inductive tree model for representing programs. It takes the form of a work library, which takes heavy inspiration from iTrees, but with added primitives for non-determinism. Just like iTrees, it has nice properties. We can use CTrees to define modular semantics that are made from many reusable parts, and to define executable semantics that can be tested against some litmus tests, for instance. Okay, in a CTree, there are 4 possible kinds of nodes. The simplest one is leaf nodes, return nodes, that just materialize the return of a value at the end of the execution of a program. Then we have the visible event nodes that represent an effect. They represent a request to the environment of the program with many possible outcomes, many possible answers from the environment. Then we have the unary step nodes that represent an internal computation. They are the counterpart for tau transitions in process algebra. And finally, and that's what's new in comparison with regular I-trees, we have the non-deterministic branching BR nodes that represent an invisible non-deterministic choice. Okay, so I'll explain in a bit more detail visible event nodes. So as I said, each these nodes represents an effect during the execution of a program. I depicted on the left an example, a small example LLVM IR program in simplified syntax, which loads a value from address A, then stores it back to address B, and finally returns 0. And I also depicted the corresponding CTree on the right. Okay, so of course, the effects that will happen during the execution of this program are memory read and memory write events. So at the root of the tree, we first have a read of A, which corresponds to the initial load. And depending on the value that is read, we take either the left or the right branch. Assuming we take the right branch, we get to the right back of value 1 to address B, and finally to the return of 0. Okay, we can go even further to make the semantics of CTree, I-tree, or CTree appear by interpreting the visible events it contains. For that purpose, we can write, we can use stateful interpreters for some kinds. I mean, for one kind of visible nodes that appears in the tree. And I depicted an example on the left of a CTree with print events and memory access events. And we would like to interpret the memory access events starting from a state in which address A is mapped to value 1, the state being a mapping from addresses to their current values. So we start from the root of the tree, and there is a visible print event. This is not a memory access, so we leave it as is. Then we get to the visible read of A. The semantics will just be to return the relevant value from the mapping. And as I said, in our initial state, A is mapped to 1. So the right branch is the right one. And so we keep this right branch and discard the other one. We trim the tree. And the visible read node is consumed. It becomes simply a unary step node. Okay, then we reach the visible write of 1 to B. And it updates our memory state so that B is now mapped to 1. And finally, we reach the return of 0. We still return 0, but we also return the final memory state. Okay, that was for an example of I-tree or C-tree interpretation of a visible event. But we can go much further than this example. And in fact, we have a general methodology to make the semantics of a C-tree appear, which is to successively interpret each kind of event nodes. We just did it for memory events, but we could do the same for the print events that were in the tree, or for other kinds of events. For instance, the Vellum project, which is based on I-trees, applies this approach to LLVM IR, which seeks successive layers of interpretation to give the semantics to the various kinds of visible nodes that represent what can happen during the execution of an LLVM IR program. Okay, and after there is no visible event node left in a tree, we can actually execute the tree or the model that we get. Because in the end, the model that we get is a function that maps an initial state to a tree that is assuming the program terminates and is deterministic, just a sequence of unary step nodes that leads to a return of the final state of the execution. So it maps an initial state to a final step. In this way, this is execution. Okay. I've not talked until now about the meta theory of C-trees. The first thing to do to prove meta-theoreticals about C-trees is to define a fitting notion of equivalence. And the way we do it is by reusing as much as possible existing literature on label transition systems, or LTSs, because we have a systematic method from any C-tree to build an underlying LTS, and then we use existing notions of equivalence on LTSs in order to reason about C-trees. And starting from this point, our main notion of equivalence is strong bisimulation on LTSs or on C-trees. And in the way we build LTSs, we are very careful to give non-determinism semantics to the non-deterministic BR nodes. This is depicted below. We can see a C-tree that is translated into an LTS, and the transitions that would correspond to the non-deterministic BR nodes are kind of collapsed. But I won't delve too much into details of the meta-theory of C-trees. It's out of the scope of this paper. Rather, I move on to our model of LLVM IR concurrency. So our source language is a small subset of LLVM IR, but a subset that still retains its concurrency features with some thread management functions from the C11 standard library for thread creation and joining, and concurrent atomic memory accesses with several levels of atomicity. Okay, starting from such source programs, we can first, of course, represent them as C-trees, and then we have an interpretation stack made of several layers of interpretation to consume the various kinds of visible events in the tree until we get to a final executable model with no visible event node left. And a first interesting result on this interpretation stack is our result of transport of equivalence. Each of these layers preserves program equivalence, meaning that if we have two programs that are equivalent at this stage, after interpretation, they will still be equivalent. Okay. So I'll now go into more detail about the different passes of this stack, starting with the representation. The actual representation procedure is defined by induction on the source syntax. It's completely standard, but what's interesting is the various kinds of events that we introduce in the C-trees. There are three main kinds of events. First, variable accesses effects with reading and writing to local variables and reading from global variables because they are read-only in LLVM IR. Then we have events to represent thread creation with a spawn event that takes an LLVM IR function and just spawns a new task from it. And finally, memory access events with load, store, read, modify, write, and fence events, each annotated with a memory ordering label. Okay, I will skip the variable interpretation pass because it's standard, and I'll move on directly to the interpretation of multi-threading. The basic idea is that in order to model the parallel composition of n threads, each represented as C-trees, we interleave their C-trees into a single multi-threaded C-tree. And in this context, at each point of the execution of the program, we introduce a non-deterministic branching node, a BR sched node, which chooses in which thread we will next perform a step of execution. I depicted an example on the right with a yellow thread and a green thread represented as C-trees, and we would like to take their parallel composition. So we have two threads, so we'll start with a scheduling sched node with two children. Assuming we want to schedule the yellow thread first, we will take the left branch and get to a load of A, which is directly taken from the left C-tree. And after having performed this first step, we go back to another sched node, which will choose whether we continue executing the left C-tree or move on to perform one step in the right one, and so on and so on. It gets slightly more complicated when there is a new thread that is spawned. Basically, subsequent sched nodes will have one more child to account for this additional running thread. And in practice, this is not implemented using a regular interpretation path, as I showed earlier, but based on a custom co-recursive combinator that we called interleave. Okay, the next and last step is the interpretation of concurrent memory accesses. In fact, we support three alternative concurrent memory models. We support the basic sequential consistency or SC model. We also have an interpreter for the total store ordering or TSO memory model. And finally, the most interesting one, an interpreter for a subset of promising semantics. And between these different memory models, we have a few simulation results to state in particular that sequential consistency is a stronger memory model than TSO and promising. The original promising semantics is a very complete operational concurrent memory model that supports many levels of atomicity, just like LLVM IR. This is what makes it interesting in our setting. And in our development, we support a subset of promising semantics with most levels of atomicity that it supports, but monotonic accesses are partly left to future work. I now detail why. Okay, so the basic idea behind promising semantics and the family of promising semantics is that in our state, we will associate to each memory address a timeline of all the past writes that have occurred at this memory address. I depicted, for instance, a timeline for some address A to which value V1 has been written, then V2, then V3. But in fact, it's a bit more complicated than just that, because for monotonic memory accesses in particular, they can be executed out of order. So maybe the write of V3 happened kind of before V2. I mean, it's I can't delve too much into detail, but there is some reordering that happens with some sanity checks, of course. But in the end, this allows to have load and store reorderings. This is supported in promising semantics, and this is supported in our partial implementation too. But it gets more complicated for load store reorderings. The actual original promising semantics supports load store reorderings. using what they call promises, which is a kind of speculative memory write. At any point of the execution, a thread can promise that at some point in the future, it will write some value to some address. And this forces us to maintain an invariant that at any point of the execution, all the promises can still be fulfilled by their respective threads, no matter what happens in the other threads, in order in particular to prevent the out of thin air problem. But this is quite complicated, and this does not play well in our setting, in our very operational setting. This would be quite complicated to represent. We would basically have to carry proof terms in our CTrees. So we do not support right now load store reorderings in our development. But if we can keep in mind that our long-term goal is to have a verified compilation infrastructure, this is not that big of a problem. Okay, so we finally get to the executable module once we have interpreted every kind of visible event. But unlike the example I've shown in the beginning, there is still some branching in our final tree because there is still some non-determinism. We have to schedule the remaining non-determinism in the final C tree. We have several schedulers that we wrote in work for that purpose. In order to schedule the remaining branching sched nodes, we have a round-robin scheduler and a pseudo-random scheduler. And in order to schedule, to choose a promising timestamp when a read or write occurs, we have two schedulers, one that always chooses a maximal timestamp, which basically gives us a sequentially consistent execution, and one that chooses a random, pseudo-random timestamp, valid timestamp. Okay, there is an alternative for executing our final C-trees, which is that instead of choosing one branch when there is some non-determinism, we could just explore all the branches and collect all the possible end results of the execution. For that purpose, we wrote a collecting interpreter in OCaml, thanks to Rock's extraction feature. And for a small LLVM program, such as the one on the left, it will output the possible final values of the execution. This is very useful to compare different memory models on small litmus tests, but of course, it does not scale very well to large programs. Okay, so in this paper, we defined modular semantics for concurrency in work with pluggable memory models, thanks to our use of CTrees, and we applied this to the subset of LLVM concurrency. Our code is available on GitHub, but this is still in early development. There is still a lot of things to do. For instance, we could prove much more results, many more results on the interpretation stack. In particular, it would be nice to have results of reordering between the different interpretation passes, saying that we could swap the orders of different interpretation passes and get the same semantics at the end. And of course, in the long term, it would be nice to merge our effort into the actual volume project. Okay, thank you for your attention.
Thank you very much. Okay, so we have a few minutes for questions.
Hello, yeah, thanks for the talk. So one thing I was wondering is you said you're inserting these sched nodes in a whole bunch of places. Do you have any way to be sure that you added enough of them? Like, is there a theorem you can state, or maybe even you have proven, that this is like equivalent to an interleaving semantics with the per thread small step reduction or anything like that?
In fact, how the co-recursive combinator is written is that it introduces sked nodes between, after each step in the label transition system. We are sure that the granularity is enough because we insert them whenever something happens in a thread.
Where in the pipeline does this happen? Because like if you do this too early, then the individual events might still be very big, and then you don't get interleavings. Again, still don't get enough interleavings, right? Like it depends on the granularity of your events.
The idea is that it happens at the beginning, but we still interpret the variable access events before because they are thread local. There is no interaction between threads when you consider register, reading, or writing. But the idea is that it happens at the beginning.
Okay, thanks.
I have a question because I'm doing weak memory models too, and I was thinking about how to apply your stuff to what I'm doing. And one thing I'm wondering is that when you do interleaving, I mean, when you represent parallelism as deterministic interleaving, you assume implicitly that all your load and store events are atomic, logically atomic in some sense. And in the i3/c3 framework, I was always wondering, is there a way as an intermediary step to actually represent those two things happen in parallel without fixing the order first?
The visible loads and store and so on events happen in some order, but their semantics can be such that it captures out of order semantics. As I've shown, we can model a large part of promising semantics, for instance. But of course, it would be possible to have more granularity by having more atomic memory access events at the perhaps microarchitectural level if we consider specific architectures. And we could introduce, in this case, sked nodes between microarchitectural steps if we had more granular events. But this is not exactly our research direction.
Yeah, no, I mean, if you don't want to do that lowering early and leave it to the precise memory model, I was wondering whether at the intermediary point you could actually represent a parallel composition, because here you are doing the switch from two threads to a non-deterministic interleaving relatively early in your pipeline, and that restricts what kind of models you can plug after that.
I mean, it could be the interleaving could happen after the memory access interpretation, given that we introduce some kind of yield events that is kind of like in Brooks interleaving semantics. And this is one of the path reordering results that I would like to prove, but I'm not sure it answers your question.
Yeah, I think you can take that offline. That would sounds like a really interesting discussion. But in the meantime, we have lunch next.
Yeah, I just
wanted to mention that we have a Discord, that there is a Discord thing for the whole conference, so you can discuss on paper. So there is already a question for Dan, the first talk after Emily's invited talk. So if the speakers can connect to Discord during the week, maybe there will be question and you can discuss over there, and it will be very nice. So you can follow the discussion over there.
Great, that's good to know. Let's thank our speaker again.